Feed a complex, multi-step workflow into a standard text-in, text-out language model, and its logic pathways will inevitably bottleneck and fracture. Traditional models are built as stateless, passive responders. They answer the exact prompt directly in front of them, requiring constant human intervention to route information from one step to the next. Agentic AI replaces this passive response mechanism with an active orchestration loop. An agent possesses the internal architecture to evaluate the high-level goal, plan the necessary subtasks, track its own progress, and execute commands autonomously. But delegating autonomy to a machine introduces a severe technical trade-off. As an AI model's independent decision-making capability increases, its structural transparency typically drops, creating an opaque black box. In highly regulated sectors like finance, law, and healthcare, deploying a black box is a non-starter. If a system cannot explicitly document how it arrived at a conclusion, compliance teams cannot approve it for production use. To resolve this tension between autonomy and transparency, we will deconstruct the React framework, examine how multi-agent systems address the explainability bottleneck, and provide a four-dimension technical framework for production deployment. Moving from simple text generation to verifiable autonomous orchestration separates a sandbox experiment from viable production-grade enterprise architecture. When standard language models hallucinate, it is because they are relying on static training weights to solve dynamic, real-world problems they have never encountered. The React framework interleaves thought with execution. During reasoning, the agent generates a step-by-step logic trace. Next, the acting phase invokes external APIs to query the environment. The agent then feeds this output back into its reasoning engine, replanning based on hard evidence. Maintaining this continuous loop without dropping context requires a dedicated memory module. A short-term memory tracks the immediate state of the current conversation window, while a long-term memory utilizes vector databases, allowing the agent to perform semantic searches and apply few-shot learning from past task executions. Integrating the React framework with external tools and persistent memory upgrades, a language model from a passive knowledge retrieval system into an active, environment-altering agent. Scaling a single monolithic model to handle highly complex reasoning tasks inevitably hits an explainability wall. We can examine this by looking at topic modeling, which serves as the ultimate test case for balancing high predictive accuracy with structural transparency. This chart plots topic identification F1 scores. Latent directly allocation hits 0.93, while BER topic peaks at 0.98. Despite near-perfect accuracy, BER topic suffers from a structural flaw. Relying entirely on contextual vector embeddings, its decision boundary for grouping texts remains an unreadable black box. Mathematical data clusters are useless to an auditor. If a system cannot generate a natural language reasoning trace justifying exactly why a specific document received a specific label, the model fails compliance testing. Achieving both high computational accuracy and absolute human explainability involves moving beyond single monolithic models and toward the orchestration of specialized multi-agent systems. The agent topic architecture uses four specialized agents. The topic identification agent assigns a topic and outputs an explanation. The review agent audits this trace, pushing valid data to a database. Finally, grouping and hierarchy agents organize topics into an interconnected thematic tree. Researchers stress-tested this architecture against the BBC News dataset, a massive corpus of unstructured articles requiring precise thematic categorization. The multi-agent workflow matched the baseline GPT 4.1 model with an F1 score of 0.95. Simultaneously, it expanded the dataset's flat 5-category structure into 2,045 highly granular topics, accurately organized across 6 hierarchical levels. In one specific test case, the architecture parsed a complex financial document detailing quarterly profit jumps and accounting restatements for Time Warner. The system accurately tagged the text under economy and finance, providing a written reasoning trace that explicitly connected the profit restatements to ongoing regulatory inquiries. Because every single node in this workflow generates an auditable text explanation, the reasoning behind every decision becomes transparent. The agent topic architecture demonstrates that specialized agent pipelines offer a verifiable method for scaling reasoning in environments where transparency is a requirement. Bridging the gap between an academic success and a live enterprise deployment requires passing rigorous security and integration audits. Technical leaders use this four-dimension radar chart to safely guide systems into production. Dimension 1 is autonomy level. An agent's independence must match the consequence of failure, demanding human overrides. Dimension 2 covers integration complexity, requiring strict permissions across legacy databases. Dimension 3 tracks regulatory impact. Compliance frameworks like the EU AI Act dictate that auditability and explainability must be engineered into the architecture immediately. Dimension 4 is data sensitivity. The scope of the agent's reasoning must be rigidly confined by internal data tiering models, preventing access to unauthorized information. Mapping a high-risk workflow, like automated customer due diligence or autonomous trading, onto this chart pushes the required operating parameters to the extreme boundaries of regulatory impact and data sensitivity. Explainable multi-agent architectures offer a robust framework for navigating the specific regulatory and data sensitivity thresholds identified in this model. As raw technical capability becomes a baseline, the engineering focus has shifted towards the orchestration of these capabilities within strict operational constraints. Replacing routine tasks with accountable agent networks frees engineers from repetitive oversight, allowing them to focus on strategic architecture and complex relationship building. Success relies on the ability to restructure organizational workflows around autonomous systems, moving past the practice of merely adding new software tools to legacy processes. Mastering the implementation and governance of multi-agent frameworks is the definitive boundary separating legacy organizations from the technical leaders of 2026.